for the next part itself, we will talk about the unstable particles. Because your particles are actually unstable, just like carbon 13 or carbon 14 itself, the thing is, you don't want to remain unstable. Everyone wants to be stable. So we will actually undergo this process called nuclear decay or radioactive decay itself. And what's so special about this is that you will actually undergo what we call a random and spontaneous process itself, where your particles, right, your unstable nucleus will emit radioactive radiation to become more stable. This is the goal that you want to achieve. So when we talk about random itself, you always want to say that basically it's so random, there is no, how to say, you can't measure when you can actually undergo decay. It will just out of the normal, maybe 1 second later, maybe 2 seconds later, maybe 100 years later. Okay, so it is quite vague on when the process will actually occur, and spontaneous itself, which means that you occur naturally, which you don't actually need external influence, which means if I place the radioactive material right on the floor in front of us, it will just automatically undergo radioactive decay just by itself. You don't need to heat it up, you don't need to provide energy to it, you don't need to do anything. Alright, then you have three different types of radioactive decay. Number one is your alpha decay itself. Now, alpha particles are basically made of 2 protons and 2 neutrons, which basically you can write it as 4 2 alpha in this case. And because you have your 2 protons, now do take note, this does not include any electrons, so you actually have a positive charge of 2. Whereas for your beta rays itself, or beta radiation, is a bit different. Beta itself will actually have it's basically made out of electrons itself, whereas for your alpha is made of 2 protons, 2 neutrons. Okay, so you can actually write your beta as your -1. Okay, so how do you have electrons? Because if you think back to what I just previously mentioned to you, you don't actually have electrons inside your nucleus. So what actually happens? What makes this electron come from nowhere? Basically, your neutron will actually become a proton and a beta particle. So basically, the beta particle comes from the neutron inside. So basically, one of your neutron will become a proton and a beta particle, which is basically a fast-moving electron. Okay? And because of the negative charge itself, you will have a -1. Now, on the other hand, your last but not least, your gamma rays. Now, gamma rays are written in this format, gamma. Okay, looks like a funny Y, but basically it is written in this way. Now, gamma rays itself don't have particles. They are not particles. They are just your EM wave. Now, remember your EM wave, the last one, the most dangerous one is gamma waves. Basically, gamma radiation is basically when I have a very unstable nucleus, which usually will be at very high energy, and when it loses all this energy and becomes a ground state, basically what it does is it emits EM wave in the form of gamma rays itself. And because you only have gamma rays, it's just rays, just pure energy itself. Because you are just pure energy, you don't actually have any kind of charge. Alright, so in the table below, some of the example you can see right now, you do notice that I write helium or electrons for this. You can actually rewrite this as 4 2 alpha and 0 -1 electron, beta. Okay, so I want you to notice that if you notice for the top part here, if you write the equation out, 234 is equals to 238 is equals to 234 plus 4. Basically, this on top, this equation, as well as the one below, must always tally. So what I mean by that is 92 is always going to be equal to 90 plus 2. So in this case, you can actually count the number of alpha particles that you emit. Because the thing is, these equations are somewhat simple, but in real life, you can have multiple decays at the same time. So I can have like 4 alphas and 3 betas. So it basically becomes very similar to your chemical equations. You just need to make sure that whatever's on your left hand side is equals to whatever's on your right hand side. So in this case, you have 3 plus 0. And this one is a bit special because I actually have one proton and suddenly I become two protons. Why? Because I will actually have one of my neutron becomes a proton and an electron. So basically you can see the number of protons increase and when the number of protons change, just like the one on top, you notice that you actually change elements. So you started with a tritium, a 3,1H helium, no, hydrogen isotope, and you actually become a helium 3 isotope itself. So you can see this is very, very different. Then for this, there's no change because your number of protons remain unchanged. It's just from excited to relax. It's like you're very, very energetic, and then once you use up all your energy, you become chill and relax. Okay? And each of these alpha, beta, and gamma rays itself, they all have different effects. And we can categorize these effects under two main groups. Your ionizing effect, which if you remember from your EM spectrum chapter, and your penetrating power itself. Okay, so do remember when we talk about your ionizing radiation or ionizing effect itself, just basically means how much damage you can deal to your living cells. If that's the very simplified version of the definition. Now, basically, if you notice, alpha particles itself, they have very high ionizing effect, but they have very, very low penetrating power. Okay, basically, if you notice that the ionizing effect and your penetrating power itself, they are actually inversely proportional, which means if I have high ionizing effect, I have low penetrating power. If I have low ionizing effect, I have high penetrating power. And one thing scary is that if you remember in your EM spectrum itself, we know that gamma rays itself, you have your X-ray, you have your UV, you have your visible light, you have your infrared, you have your microwave, you have your radio wave. This is the most dangerous. But in terms of radioactive radiation itself, this fella here is actually the least dangerous. Which means that if you add on the alphabets itself, alpha is extremely, extremely dangerous itself. So if you're ever exposed to alpha radiation, your cells almost immediately will actually be ionized and die. And worse, cancers form almost instantaneously. It's very, very dangerous itself. But thankfully, the world likes balance. So if you have very harmful, dangerous effects, you can actually be just stopped by air. Okay, literally, if alpha particles travel in air, just a few cm and then they become harmless. So that's the thankful thing that we have for your alpha radiation, because alpha radiations are very, very harmful, but they can only travel a very, very short distance. Whereas for your gamma rays, they can travel very, very far. So you can see all the things that you can stop using this. Now, it's not a must that we use aluminium for beta. We can use cardboard, we can use other metals, but typically, the denser you are, the better it will be at stopping it. So it really depends on what we're actually using. So you can see for this, for example over here, if I have your radioactive source X, Y, and Z, what can we say about the radiation for this? So you can say that source X is basically your alpha, because you can actually be stopped by paper. And Y would be your gamma radiation, because it can't be stopped by any of them. And the thing is, last but not least, would be beta radiation itself, because it will be stopped by aluminium. Now, one thing I forgot to mention earlier just now is that this word here shouldn't be stopped. This word should be reduced, because there's actually no way for us to stop gamma radiation. Gamma radiation is an electromagnetic wave, right? So don't forget, it can travel through almost any medium itself. So solid, liquid, gas, and even your vacuum. So there's no actual way to stop it. You can only reduce the amount until it's insignificant. Okay, so do take note of that. And then you have americium nucleus decaying into this. So what you want to just write is 24195 americium and arrow, and you become 23793 neptunium. Okay, then you ask yourself, what changed? 95 minus 93, I'll end up with a 2. 241 minus 237 is 4. This one will be an alpha decay. So in this case, this was a alpha decay. Okay, so whenever they ask you for this kind of thing and ask you whether which type of radioactive decay we're dealing with, very straightforward is we just write down the equation itself. So you can see 32 on top, there's no change, it's 0. This one you can see increased by 1, so I need to minus away. This must be a beta decay. So this is the answers for these two questions.